So in this video, I'm going to be going over the electrophilic aromatic substitution, and I have about 16 problems. They're ranging from really easy, like the one on the board right now, to some more challenging problems where it actually requires a good bit of thinking for them. Again, I know I talk a lot, so as usual, there'll be timestamps for when the problems start and when the solutions are given. Also, I will have the PDFs for the problems and solutions down below in case you prefer doing that instead of watching the video. Anyways, let's go into the first one I have on the board right now. It's a simple halogenation. There's not going to be a lot to it. We know that if we have bromine, and sometimes you dissolve it in water, whatever it is, but then you have some rusty nail, so this iron means right here, and when you combine it with benzene, you will halogenate one time. So this would be what you get when you combine bromine, some Lewis acid catalyst, and benzene. So on this problem, another really easy one. We're just combining benzene with sulfuric acid, and this thing up here at the top is, we're going to refer to it as fuming sulfuric acid. And so go ahead and try this problem real quick, and then we'll work out the solution. So for this problem, you don't actually need the fuming sulfuric acid here. Sulfuric acid will work just fine on its own as long as it's concentrated. But when you combine these things together, you will get sulfonation happening. So just like that. It's another really easy one. Let's go into a little bit more challenging problems. Okay, so for this problem, we have, in this case, an alcohol that we're going to mix together with benzene and acetic acid. So give this one a try real quick. All right, so now that you've tried it, first thing that's going to happen here, we can tell our acetic acid is going to protonate our alcohol, which now creates an electrophilic carbon. So allowing that benzene ring to attack that, that carbon, you'll actually replace the oxygen and you'll end up with this product over here. That looks just like this. And that's your product. Let's go to the next. So here we're mixing aluminum chloride with some alcohol halide and benzene. What would the product look like? So for this one, this is a kind of standard Friedel-Crafts alkylation. So we can anticipate that the product is going to look just as it would if you replace the chlorine with benzene attached where the chlorine is. So what does that look like? Well, there's your benzene ring right here. And then we said we're just going to replace that chlorine with that benzene ring, which leaves us with that. So we notice that these two products are actually the same thing. All right, on this problem, another similar setup, we have, actually this is an acyl chloride, and again, reacting with benzene and a Lewis acid catalyst. So give this one a try. So this is a standard type of example for a Friedel-Crafts acylation. So purposes for doing Friedel-Crafts acylation over Friedel-Crafts alkylation. In the previous problem, I just drew one substitution happening, but it's actually true that you probably get more than that one substitution, probably get some byproducts. But in the Friedel-Crafts acylation, like what we've had drawn right here, you avoid that issue. And the reasoning is that we are effectively deactivating our aromatic ring the second we put something that's electron withdrawing on it. So we refer to like methyl groups and alkyl groups in general as being electron donating. And we know electron donating things activate aromatic rings. And so that's why Friedel-Crafts alkylations actually aren't used quite as much as Friedel-Crafts acylations, because you have more control. And that's what we've demonstrated here in this problem. Okay, so on this problem, it's just standard phenol and bromine reaction. So give this one a try. So the takeaway here is that I've written that the conditions are cold. So underneath that bromine, underneath the bromine right here, I've said cold, which is important to us because that tells us that any sort of halogenation that's going to happen is actually going to be significantly decreased in the amount that you'll get. So, in other words, if the conditions were room temperature, or if for some reason you heated it up, you'd actually get multiple halogenations happening. So, uh, lowering the temperatures in this reaction is a good way for you to get just one product with one substitution. So, our product would look like this. And I guess I should note for the rest of the video, I will be putting my substitutions, so my electrophilic aromatic substitutions, always at the less sterically hindered position. So in some cases, actually, it is more favored that the ortho position is over the para position. But often, sterics have a significant effect as well. And so it's a safe assumption just to assume the para position if you aren't given values for the ortho or para. So that's why I've substituted on the para position here. So let's go on. On this problem, kind of testing that idea that we just talked about in the previous problem, actually. So look at this one and give it a try, and we'll talk about it in just a second. So it looks exactly the same, and in truth it is, except I haven't specified the temperature, so we are to assume it is at room temperature here. So assuming it's at room temperature, we know phenol is a very activated aromatic system, and that's because this oxygen is donating so well to that benzene ring. So because it's activated, when we put one halogen on, so if we put one halogen on right here, and the temperatures are at room temperature, we're not going to see that stop. We're going to see it keep going. Uh, we're not lowering the rate of the ring here. So respective to benzene, so if benzene's rate was 1 and phenol was something like 100, then at room temperature, when we just put one halogen on, well, that's not going to bring the rate back closer to 1. So we'd actually see bromine be substituted on every position possible here. And so this is what we would expect for the product if we did this at room temperature. So this one's also a very similar problem. We still have that oxygen that looks like it'll be donating, but I've just changed up a little bit here that hopefully gets you guys to think. So give this problem a try real quick and we can talk afterwards. So the major thing that's interesting to note is that, yeah, the oxygen is going to play a similar role like it did in the above problem with phenol. This other stuff that's actually attached to the side of the oxygen right here that's directly attached to the benzene ring actually has no significant effect that we are going to worry about in respect to the rate of the reaction. But we do need to consider some molecular orbital theory. Nothing too advanced, it's just recognizing that the p orbitals on our benzene ring are going straight up and down, and this carboxylic acid that's attached through a carbon and an oxygen to the benzene ring is kind of hanging out to the side. So the reason I mention the p orbitals is that this carboxylic acid is going to struggle to go from the right side to the left side, because in order to flip back and forth, you'd have to be going over that p orbital system, which is going to be really big and bulky, and especially with the carboxylic acid that's sticking out, extra H and some of the lone pairs on the oxygen. And there are going to be issues trying to move your orbitals across from each other without getting them to interact. So you can kind of think of it as this carboxylic acid part right here being just stuck in place. So it doesn't really move to the left side. And what that tells you is that this chlorine will get substituted onto that ortho position and this para position as well, but you won't see a chlorine get substituted. You won't see a chlorine get substituted right here. And that's because the steric issues from this carboxylic acid is just too much of an issue to get that chlorine in there. And it can't flop over or maybe go perpendicular to this oxygen, because putting it perpendicular would put this oxygen and this hydrogen in the way of the delocalized system of the ring. which is a bad problem. So as far as this problem goes, you only get 2 substitutions for your chlorine here. So on this problem, we have a standard, looks like phenol, with the para position being substituted with some nitro group. We're going to hit with some hydrogen with palladium on carbon, and then whatever solvent you chose to use. So figure out this first intermediate, and then I'm going to extend this problem just a little bit further after that. So the first part that we're going to do should be pretty straightforward. The only thing that hydrogen with palladium on carbon could do here is not reduce the benzene ring. It's too high up in energy to do that. But if we reduce the nitro group, we'd be left with an amine right there. And so that's what this first step would do. But if I want to carry this over and actually attack it with acetic anhydride, which is what this stuff looks like. So acetic anhydride, that's not it. That's acetic anhydride. So if we let acetic anhydride fall into the mix here, what would happen here? So here, adding acetic anhydride, you obviously have this huge delta positive right here, because every carbonyl does. And so we have 2 different groups, an alcohol and an amine, that could potentially attack that position. So we have to determine, is it going to be the alcohol or is it going to be the amine that attacks? Well, amines are more likely to give up their electrons because they're better bases and generally better nucleophiles. And so we'll see the amine attack that delta positive part of the carbonyl to give us this right here, which is an interesting problem because this is actually how they industrially make acetaminophen, just like that. So on this next problem, we're going to do some nitric acid, sulfuric acid, and whatever this stuff is hanging off of our benzene ring. So what would our product look like here? So the whatever this stuff is actually just, to us, boiled down to an electron withdrawing group. We have 2 of the most electronegative atoms attached to carbon, which are going to be pulling on that carbon, making it feel more positive, which makes it feel electrophilic to, or electron withdrawing to the benzene ring. So because it's electron withdrawing, we're going to treat it as such. And so that means that our substitution that happens here is going to actually be at the meta position. So here's the meta position. Now, it is the nitro group that's getting substituted on. You might have a very small percentage of the sulfonation happening. But a bigger thing to note is that if I didn't add sulfuric acid here, this reaction wouldn't work because nitrating on deactivated rings does not work unless you have something to speed it up. So in this case, the sulfuric acid was our thing to speed it up. Okay, so on this problem, we're just going to be using nitrobenzene with 2 different types of reactions with bromine. So give it a try real quick. For this problem, the first one we should recognize from the reasoning with the last problem is that halogenation is similar to nitration. It will not work if the ring is deactivated. So for right here, we should expect there to be no reaction. Now, if we actually add a Lewis acid catalyst, so in this case, aluminum chloride, we can get it to work on deactivated rings. So just as we would expect, it would be substituted on to the meta position, just like this. All right, so here's the next problem. Go ahead and give it a try real quick. So with this problem, we can recognize very simply the most obvious thing would be to do a Friedel-Crafts calculation. We need to recognize, though, however, that Friedel-Crafts calculation allows for carbocation rearrangement if that is favorable. In this case, it is. So instead of attaching it such that we'd have a propyl group, we're going to attach it such that we have an isopropyl group. So that's what we should expect. And however, we shouldn't stop right here. We should also note, just to cover our bases, that we'd also expect maybe a little of the para-substituted isopropyl groups, and then any other byproducts. So maybe they substitute again at the ortho position. So uh, to be very broad, I'm just going to say other byproducts here. So I put this problem in because we should recognize that Fieldcross alkylations, although they can put things onto benzene rings, they didn't put the chloro or chloropropane group onto the benzene ring the way that it started out as. So if we wanted to actually make what we have drawn on our product, then that's great. But if we actually didn't want it to do that, if we want it to be the way it was represented in the reactants, like chloropropane, that wouldn't be accomplished here in this process. The other issue with the Fieldcross alkylation is that we can double or even triple alkylate, which is another issue if we don't want that to happen. So I threw this in here so that we can recognize that although Fieldcross alkylations are good in the right circumstances, Fieldcross acylations are often used because we can control them more easily. All right, so here's the next problem. Give it a try real quick. For this problem, we're going to treat or allow this oxygen to actually work as our electrophilic group. So it's going to attach itself to its Lewis acid. When it does that, we can expect that some of the electrons from our benzene ring will attack the carbonyl. When it does that, it's going to open up this ring. So if you followed all that, the big thing there is open up the ring. We should end up with something like this happening. So let me make sure I have all my 1, 2, 3, 4, 5. So I do have the correct number. And so this is, again, when the aluminum chloride attaches itself to the O single bond to the carbons. One of the double bonds from the benzene ring will attack the carbonyl at either this delta positive position or this delta positive position. When it does that, the 5-member ring will eventually open up. When it opens up, you can go through the normal electrophilic aromatic substitution process where you then have to pull off a proton from the ring to reestablish its aromaticity, and that proton will get placed over onto this oxygen over here on the right, which forms its final carboxylic acid. So 2 more problems, more tricky problems that are actually quite fun. So let's get to those right now. Okay, so on this problem, I've kind of changed up what I'm asking. But given hydronium, acetic anhydride, sodium hydroxide, and carbon dioxide, and their respective solvents, can you turn phenol into its product that I've depicted over here on the right? So I just want to try real quick and then we'll talk about it. It may take more than one step, but that's okay. Okay, so jumping straight to the chase, the first thing I'm going to want to do is to add sodium hydroxide. I'm adding sodium hydroxide because I want to pull off this proton off of phenol right here, because that will give the ring, it'll make the ring more activated because that oxygen will now have a negative charge and it will allow the ring to do then what I want it to do. So let's do this real quick. That would look like this right here. So since the ring is very activated, I'm going to introduce carbon dioxide. So carbon dioxide will substitute at the ortho position. And in truth, you probably get a little bit that goes to the para position. That isn't something that you should know. It's just, unless you're given the values, you wouldn't know that it goes to the ortho position exclusively. And it doesn't go exclusively here, but a good portion of it in this particular case is actually ortho position. So it's an okay suggestion to suggest it this way. I've added one too many H's. There should be a negative charge right here and a sodium ion right there. So I've used sodium hydroxide, I used carbon dioxide. Next, I'm going to use hydronium. So that arrow is a little bit longer than I needed. Use hydronium just to protonate this carboxylic acid derivative. And now if I introduced acetic anhydride, the easiest thing for acetic anhydride to be attacked by is that, that solo alcohol. So the one that we started with that looks like phenol. So introducing acetic anhydride, we can get all the way to the product. So interesting little product, and this is actually a drug. I believe it's aspirin. So a cool little problem here. Okay, so for this problem, you could use whatever you wanted. Just get aniline to parabromoaniline. So give it a try real quick, and we will talk about it afterwards. So for this problem, the issue with simply adding bromine right away is that you will over-halogenate. So you get the para position in both ortho positions, which is an issue. It's not something that is good here, as if we would just want the single substitution occurring. So we need some way to deactivate slightly the aniline. And the best way to do that is to introduce acetic anhydride. So we've been using it a lot. Acetic anhydride will do what we expect it to do with aniline, creating something like this. Now if we introduce bromine, this ring is slightly less activated, although it is still more activated than it is deactivated. So introducing bromine now will halogenate in the para position. It just will not over halogenate, which ultimately was the goal that we were trying to get after. So, and there's our bromine. And then getting all the way back up to the product, obviously we have to replace this carbonyl with just an H so we can get the aniline derivative back. So introducing something like some acid, so I'm going to use hydrochloric acid, will actually get us all the way back to our product that we wanted.